Hello everyone, my name is Menuhin, and in this talk I'll tell you about a paper that I've co-authored with Naor. It's called Shuffling Cards When You Are of Very Little Brain, Low Memory Generation of Permutations. And as the name suggests, it's about generating random permutations with a small amount of space. We start with a thought experiment. Say the numbers 1 through 5 in some random order. Should be easy. 1, 4, 5, 3, 2. That's doable. Now, do the same for 1 through 100. But you are not allowed to err. You must say each number exactly once. You might feel an urge to grab a pen and a paper, but it is forbidden. You might think about some clever way to come up with the next number, say, permute the first 5 numbers and then proceed to the next 5 numbers, but how random is that? And if it is, how do we measure it? Permutations are a fundamental object. The task of generating a random permutation has been studied in crypto, in the circuits literature, combinatorically, and so on. We study the memory requirement for generating permutations, and we do that through a realization of card guessing game. Card guessing is a game played between two players, a dealer and a guesser. At the beginning of the game, the dealer holds a deck that consists of n cards. In each turn, the dealer picks one card from the deck and places it face down on a table, so no one knows which card it is. The guesser tries to predict the identity of the card and declare their guess. The card is then revealed and discarded, so the dealer may not draw that card again. The guesser gets a point for each correct guess, and the game continues until the dealer runs out of cards. The question is, how many cards were guessed correctly? And since the game is random by nature, we are interested in the expected number of correct guesses. Say that the dealer has perfect memory and can generate any permutation uniformly at random. The guesser predicts the first card with probability 1 over n, the second with probability 1 over n minus 1, and they know the last card for certain, so they guess it with probability 1. From linearity of expectation, we get that the expected score equals to the harmonic sum, which is roughly ln n. This is taken from a textbook on algorithms by Kleinberg and Tardosh. In the paper Keep That Card in Mind, Card Guessing with Limited Memory, Menuhin and Naor studied the case where the guesser has bounded memory. And in this paper, we consider the other case and ask about the relation between the amount of memory that the dealer has and the expected score. We think about the dealer as having m bits of memory and access to some source of randomness. The random bits are used on the fly, so if the dealer would like to look back at them, then they need to store these bits in their memory. In each turn, the dealer uses their current state and randomness to come up with the next card to draw and update their memory state accordingly. The dealer may also take the guesser's guesses as input. We assume that the guesser is familiar with the dealer's way of work, and we consider both the open book case, where the dealer exposes their memory, and the closed book case, where the dealer's memory is hidden. In both cases, on-the-fly coins are secret. Here is a basic dealer for example. It is taken from Knut's The Art of Computer Programming, and it is attributed to Fisher and Yates. Initially, this dealer writes all numbers explicitly in an array. In each turn, the dealer picks a random cell, draws the card written in that cell, and replaces its content with the content of the last cell, and ignores that last cell for the rest of the game. This dealer takes n log n bits of space, and each draw takes a constant time. Each available card is drawn with equal probability, so the resulting random permutation is uniform, and the expected score is ln n. Another dealer that is more space efficient is the bitmap dealer. This dealer associates a bit to each card to indicate its availability. In each turn, the dealer samples a card and asks whether this card is available for drawing. If it is, they draw it, and if it isn't, they keep sampling until an available card is found. The process of repeatedly sampling until a suitable object is found is called rejection sampling, and we will encounter it more in this video. We are thinking about the random tape as dictating the samples that the dealer perform. In this example, the dealer first checks whether 2 is available. Since it is, they draw it. Next card is 3, which is also available, so we will draw it second. Next, we are checking 3 again, see that it is not available, so trying again with 1, which is our third card, and so on. This dealer uses n bits of memory and generates a permutation uniformly, so the score is ln n, but from coupon collector, it would take n log n samples until we find the last card, so the runtime of each turn is super constant, even amortized. We'll get back to this dealer later. In this paper, we showed that there is a tight trade-off between the amount of bits that the dealer has and the score that a guesser can achieve when playing against such a dealer. We present a dealer with m bits of memory against which any guesser scores at most n over m plus ln m points in expectation. This dealer is efficient and runs in constant time. This is accompanied by a lower bound that shows that for any dealer with m bits of memory, there is a guesser that scores at least n over m points. This guesser is not necessarily efficient. When we ask that the guesser will run in a reasonable time, we notice a separation between the open book case and the closed book case. In the open book case, the guesser can run efficiently similarly to the dealer. However, in the closed book case, the dealer may use cryptographic building blocks, so the best that an efficient guesser can do is to guess from what they know and score ln n plus a negligible. Another contribution of ours is a perfect dealer, namely one that uses order n bits of memory, runs in constant time in the worst case, and generates a uniform permutation. This bridges the gap between Knut's dealer that uses n log n bits and runs in constant time and the bitmap dealer that uses n bits and runs in super constant time. We will start with discussing the low memory dealer and then show the crypto-assisted one. Instead of tracking the deck in its entirety, we split it into small mini-decks. In each turn, we pick a mini-deck at random and draw the card that reside at the top of the mini-deck. So to tell the next card, we only need to know how many cards were drawn from each mini-deck. If the mini-decks progress arbitrarily, then there is not much saving from this method. Even worse, some mini-decks may deplete early and make our dealer more predictable. But if the mini-decks progress together, then the dealer maintains its unpredictability, and we can save space by tracking their distance from some central point, like the average. So we want the mini-decks to progress somewhat evenly. This is exactly the kind of problems addressed in the classical balls into bins model, where a stochastic process is tasked with placing n balls into d bins, and the question is, how does the load distributes between the bins? There are many allocation schemes for this task, and the one that we use is called adaptive threshold, and it was introduced by Berenbrink, Chodamoradi, Zauerwald, and Stauffer. This allocation scheme can be briefly described as place a ball in a bin that is at most the average plus 1. And the way that we find such a bin is by performing rejection sampling. They showed that despite the rejection sampling, allocating n balls take order n time in expectation. We have adapted their mechanism and showed how to implement it efficiently so that each allocation takes a constant time in the worst case, and use it for our dealer. So what our dealer does is splitting the deck into D mini-decks, and for most of the game, in each turn, sample a mini-deck following the adaptive threshold allocation scheme. So we pick a mini-deck that made a progress that is below the threshold. And when only a few cards are left, we shuffle all the remaining cards and draw them one by one. For the main phase, we need to show that we can track TED-off M mini-decks, and that in each turn there are TED-off M mini-decks that are below the threshold, so we can draw from them. This implies that a guesser's probability of guessing correctly is order of 1 over m, and from linearity of expectation across the turns, that any guesser scores at most order of n over m through the main phase. Additionally, we need to show that each turn can be executed in constant time, and of course the equivalent requirements for the final phase. In the next slide, I'll prove that it is possible to track TED-off M mini-decks in an efficient manner. So D is the number of mini-decks, and let T be the turn. Let xit be the distance of mini-deck I from the threshold at turn T. Given the turn and the distance, we can conclude the number of cards drawn from this mini-deck. We claim that in each turn the total sum of distances is at most 2D, and the reason is very simple. At the beginning of the game, the threshold is 2, and all mini-decks made 0 progress, so the total sum of distances is 2D. In each turn, we draw a card from some mini-deck, and making it one card closer to the threshold, so the sum decreases by 1 in each turn. Now, after drawing D cards, the threshold grows by 1, so all mini-decks are getting one step farther from the threshold, so the sum of distances increases by D. So every turn the sum of distances decreases by 1, and every D turns it increases by D. So overall, the total sum of distances is always between D and 2D. And this means that we can encode the distances in Unary, and we would still be able to track TED-off M mini-decks. But that wouldn't be efficient. So instead, we encode the distances using alias delta encoding, or any other equivalent encoding, and we store them in a variable bit length array that allows us to access and update the content of cells in constant time. Plugging the encoding length in, we get that we can track TED-off M mini-decks throughout the game, and to do that efficiently. And that's all I'll say about our low memory dealer. As for our impossibility result, we present an efficient encoding scheme that captures the course of the game, by utilizing the fact that the dealer is not allowed to repeat the same card twice. We conclude that a dealer with low amount of memory plays a game of low entropy. We then introduce a guesser, called the myopic guesser, which exploits low entropy by simply guessing the most probable card. We show that for every dealer with m bits of memory, this guesser scores at least n over m points in expectation. The myopic guesser is not necessarily efficient. If we ask the guesser to run in polynomial time, then we see that there is a separation between an open book dealer and a closed book one. If the dealer is open book, then the myopic guesser can be as efficient as the dealer times a polynomial. Since the guesser can observe the dealer's memory but not the randomness, then they can simply simulate the dealer on multiple random tapes and estimate the most probable outcome with high probability and with a tolerable error. But if the dealer is closed book and is allowed some secrecy, then we show that there exists a dealer that uses a small amount of space against which any polynomial time guesser can score at most ln n plus a negligible. I'll show one of the two constructions that we show in the paper, and the construction I'll show can be easily explained by looking at the bitmap dealer. So what I'll show is how to implement the bitmap dealer with no bitmap. The order of cards is obviously dictated by the content of the random tape. Observe that the ith card that we draw is the ith unique card that appears in the random tape. So instead, we will use the random tape as a seed for a cryptographic pseudorandom generator, and we will generate a sufficiently long sequence of bits and refer to them as dictating card numbers, just as we originally did in our random tape. Now, in each turn, we check what is the next number that appears for the first time, and we will do so by scanning the entire pseudorandom string from the beginning. So our algorithm now looks like a nested for loop, where for each number we scan the entire string from the beginning and see whether this is the first time that it appears, and if it is, then we draw it, and otherwise we continue to the next number. So what we want is a cryptographic pseudorandom generator G' that expands k bits to something much larger, say a polynomial of k. And we want this PRG to use only order of k bits for its evaluation, and we want the scanning to be efficient because it's something that we'll do all the time during the game. So assume that we have a PRG that expands k bits to 2k bits, then we can construct a PRG as desired by iteratively applying this PRG in a way similar to the GGM construction. So think about a lopsided tree where each node is an application of the given PRG, and the right child of each node is used for the output of G', and the left child to keep iterating and producing more and more outputs. So iterating over this tree requires order of k bits, and scanning it entirely requires order of n applications to the given PRG. And this concludes our bitmap dealer that uses no bitmap. We present a more efficient construction in the paper, and I encourage you to check it. So just to wrap everything that we talked about in this video. Those who generate a random permutation and cannot remember the past are condemned to repeat it or to be predictable, unless they play against a polynomially bounded guesser and they know how to keep a secret, in which case they can use cryptography. Thanks for watching.